but it's the reading of the curves and the shifting of the whole design into the kind of artistic world of design that generates creativity and new ideas, in my mind anyway. I don't think you can look at an equation and you can see a new idea from it, but you can look at a curve and you can see, you can start to feel the circuit. And some of you that have been doing this for a long time and go in the lab a lot and blow things up and make measurements, you get intuition when you work that way rather than just being theoretical, analytical all the time. So Nicola checks all of those boxes, and I don't know if you look through his presentation yet, but he's done a super job on getting this ready. I'd like to really thank you for that, Nicola. And I'm just going to hand the presentation straight to you. I think it's going to last a little bit more than an hour. We'll be here as long as we need to try and answer all your questions. And it's going to be a great experience. So go ahead, Nicola.
Okay, thanks. Hi, good afternoon, everybody. Good morning, everybody. And thanks for your kind words first. So what I'll do today is to show you all a different approach related to how to properly design an LLC converter by using scaling laws plus a graphical approach. So the intent here is to give a different cut, respect the classical literature or the common approach. Hope you will appreciate it. So back to basics. What is the meaning of LLC? LLC string identifies a circuit combination of two inductors, one capacitor, placed somewhere in your power stage. LLC belongs to the resonant converter family. Resonant conversion is not something new, in sense there is a lot of related documentation published a long time ago. And this article, for example, comes from Prof. Steigerwald and demonstrates how LLC converter design was a hot topic even 30 years ago. The main issue about this topology is related to the fact that the literature is not always efficient, in sense that there is too much math and sometimes wrong assumptions made before starting the design. And this demonstrates how even in 2020, its analysis is still considered complex and sometimes poorly understood. But despite that, if you correctly design the LLC, it assures zero voltage switching and zero current switching somewhere in your power stage. We will go into this in a while. These features can significantly improve EMI performance of your circuit and the overall efficiency over a wide load range. For sake of simplicity, let's focus on the turn-on mechanism to explain the zero voltage switching and on the turn-off mechanism to explain the zero current switching, just for sake of simplicity, but I mean, the concept can be reversed or extended on the complementary transition. So actually, zero voltage switching at turn-on means turn on the FET after its drain to source voltage become low, allowing then and only then the current to pass through the switch. By the other side, zero current switching at the turn-off means turn off the FET after its current becomes low, allowing then and only then its VDS to increase, the drain to source voltage. How we can do that? First, we need the current to run back and forth into the power stage. This actually occurs naturally in the resonant topologies. And this is the reason why best candidates are half bridge, full bridge, and push-pull topologies. Second, the input impedance must appear inductive to the voltage source. This is a tricky concept, so I need to open a little digression here. Why the input impedance needs to be inductive? Let's imagine, for example, the half bridge inverter stage in which we have two FETs in totem pole configuration. Okay, and let's assume for simplicity that the one on the top FET is conducting, while the one on the bottom is not conducting, so high VDS. Assume now I switch off the top FET, having in this case both FETs off for a very short time. Having a lagging current or inductive current helps to discharge the parasitic capacitor of the bottom FET, in this case, forcing, after a certain amount of time, its body diode to conduct, and consequently to bringing the drain to source voltage of the bottom FET to be very low. It is in that time, so once the bottom FET VDS becomes low, it is in that time that is convenient to switch on the bottom FET. This is the reason why having a lagging current or inductive current, as you want to call it, is very important. And the third point is that to do that, so even having a lagging current, the dead time between the two consecutive MOSFET turn-on transitions should be long enough, in the sense that it is not sufficient that your current is lagging, but you need to guarantee let's say, sufficient that time in order that the previous bullet, the bullet number 2, can be achieved. Back to basics a bit. If by using SPICE or SPICE derivative simulator, I plot the inductor impedance and the capacitor impedance, I get the plots that are reported on the right. The scale is log scale. This is the reason why you see not a linear graph. If I place both of them in parallel and I repeat the measurements checking the input impedance, I get something completely different respect to the previous case. The plot is reported on the bottom right. Here, so when I place LC in parallel, you know, they are forced to have the same voltage, plus they have the same impedance at the resonance. Here is something slightly lower than 200 Hz for this example. So they have same voltage, same impedance at the resonance, but at this frequency, they have the same current because the impedance is the same, the voltage is the same, so they have the same current in amplitude because it's Ohm's law, is nothing complicated. But these current are 180 degrees out of phase between each other. So they cancel out. This is the reason why the voltage source, when you place these two components in parallel, this is the reason why at the resonance, the voltage source at the input does not see huge currents. And this is the same reason why the parallel LC offers a very high input impedance at the resonance. So first question, where do I get zero voltage switching? According to the statements we made before in the previous slide, we get zero voltage switching when we work into the inductive zone. What is the meaning of inductive zone? Actually, if we see the bottom right plot, we see that we have zero current switching on the left side of the resonance. At the same time, what is the main drawback of this structure? The main drawback is, simple answer, the main drawback is that it is not so easy to regulate the output voltage because the load is connected in parallel to the input source. So let's say the load is forced to have the same voltage. It's not easy to get voltage regulation. What about the LC series? Actually, moving to the complementary configuration, that is this one, and repeating the input impedance measurements, we get a complementary behavior. So here, the inductor and the capacitor are forced to have the same current because they are in series, and the same impedance at the resonance because the single impedance doesn't change. So at this frequency, they have the same voltage in amplitude. Due to Ohm's law, it's nothing complicated, but these voltages are 180 degrees out of phase. This is the reason why voltages on L and C in series LC configuration tends to cancel. And this is the reason why the input, the source does not see huge current because the input impedance is very low at the resonance. Same discussion here. Where do I get zero voltage switching? So according to the statements we made before, I get zero voltage switching when I work on the inductive zone. So the input impedance phase that you see on the bottom right suggests we need to stay on the right side of the resonance. At the same time, why this structure is better than LC parallel? Simple answer here as well, because the fact that we create in a certain way a voltage partition between the input and the output, eventually placed here in parallel to the inductor, allow us to gain a certain grade, let's say a certain grade of regulation by simply changing or simply playing with the input signal frequency. What is the main drawback of the LC series? Let's jump to the next slide because it was not so easy to explain in the same slide. So let's first, before thinking about cons of LC series circuit, let's assume we first map the equivalent load by using the parallel to series transformation, placing the parallel resistor in series to the inductor, just to address our circuit to something, let's say for now, similar to the LLC, but not complete. First issue with the LC series configuration is the frequency, in the sense that once, for certain reasons, we are called to get load regulation, switching from heavy load to light load, the frequency is called to increase to maintain the same gain. And what happens if I go to work at very light load? We get more losses, we get thermal problems, we get efficiency issues, this is what in related literature is called light load limitation. No? The second issue that we have seen from the previous slide is that if we work near the resonance, the input impedance is very low in this kind of configuration. It means that the voltages and currents can be extremely high in the series LC tank, and we can damage the switches or results in, let's say, in a very poor efficiency. For sake of simplicity, you can find the load regulation rule on the bottom right. So if the frequency increase, the load current decrease, the frequency need to increase to get the same gain. Why the same gain? Because we are trying to get voltage regulation. What happens if the bus varies? Actually, an easy way to mimic a bus variation into this simple circuit is to insert into the loop a voltage controlled voltage source. So we see here when the input voltage increases, the transfer function module increases. In this case, to get the same tank gain, I'm forced to increase the frequency to maintain the same gain, so to get voltage regulation. So first lesson to bring home is this one. Careful here. Each time there is a certain event for which the output voltage tends to fall, so tends to decrease, the controller should be ready to decrease the frequency, because only decreasing the frequency you are able to increase the gain, and so getting voltage regulation. Let's try to recap this point, because the regulation in LLC is not so intuitive. So if we recall the load changes, if the load increase to get the same power, the voltage needs to fall. So if the voltage falls, we need to increase the LLC tank gain. The only way to do that is by reducing the frequency, as we have seen before. And the reduction in the frequency gives an increase in the gain. At the same time, if the input voltage falls, the tank voltage, that is basically the voltage you see here on this resistor, so if the input voltage falls, the tank voltage falls. But to get voltage regulation, the tank gain shall increase to compensate, let's say, to compensate this effect. So we need to reduce the frequency, and this is the basic mechanism to control whatever LLC you design all the time. So make things easy. we start, so LLC benefits of LC series circuit advantages, trying to fix what we have called light load limitations. Okay, so this structure can be obtained, for example, by placing a larger inductor in parallel to our actual load. So we started from the LC series circuit, then we have added a parallel load, then let's say by using the parallel to series transformation, we have placed the parallel load in series to the inductor, and then we have applied a bigger inductor, getting what is called the LLC seed, the kernel. Now, let's enter into the core. No? So we have our seed. We have understood that the seed is obtained by the LC series is an evolution of the LC series converter. So let's enter into the core of the LLC seed by sweeping the load. So actually I'm sweeping the load resistor, this one. What happens here? Actually, remember that all the time that you sweep something in the tank, you need the voltage gain and you need even the impedance phase. So how can I check the zero voltage switching and zero current switching zone? Simple answer here, guys, is always the same approach. There is nothing complicated. It's always the same criteria. Looking at the input impedance phase all the time. So here we can see two resonances. One set by both L1 and L2 with the capacitor. That is the one at low frequency, this one, basically. The other one set by the smaller inductor, so L1 and the capacitor, this one. Below the lower resonance, we have the capacitive zone because the impedance is always lower than zero. And zero, yes, impedance phase. And beyond the higher resonance, we have the inductive zone. But what happens in the middle range? In the middle range, between both resonances, we have the hybrid zone because we have some loads for which I have a phase of the input impedance that is greater than zero and a phase that is lower than zero. The best zone to get zero voltage switching is identified as the central frequency range, this one, being sure the input impedance phase is always greater than zero. Note, I need to open a little digression on this point. This doesn't mean that you cannot go beyond the higher resonance. There are tons of designs made working beyond the higher resonance instead of working in, let's say, the middle frequency range. No, but you should simply be careful to work beyond the higher resonance because you can lose some advantages that you get by working in the central zone. That is this one. We will discuss later about this point. So we have swept the resistor. What happens if we sweep the greater inductor? So let's now attack the same LLC seed by sweeping the greater inductor. Okay. So on the top graph there is the voltage gain, and we see here how decreasing the inductance, so passing from the yellow curve to the red curve, we get a much lower frequency span to assure the same gain. The reason why, by the point of view of the bus swing, the red curve is better in the sense that it's able to give the same gain of the yellow one, but in, let's say, in a much lower frequency span. At the same time, if we look at the graph on the bottom, we see how a higher inductance, so the yellow curve, gives a much higher input impedance in the frequency range, under discussion. So according to Ohm's law, if the bus voltage is locked, we get lower circulating currents if the ratio of the inductance is high. So let's say if the ratio of L2 and L1 is high, we get lower circulating currents. Assuming to proceed this way, so by keeping the higher inductance ratio, so with working with L2 here, 900 milli, so working with the yellow curve, we see how working near the higher resonance, the A point, that is this one, where is this one, is identified as the best point because the impedance is higher than all the other cases. Obviously, this is valid assuming to work in the middle frequency range, enclosed between both resonances, while the point B is the worst because the impedance is lower than the point A, so higher circulating currents respect the point A. Little digression here as well. What happens if we insert the magnetics? Are these statements true or not? Let's think about it. But the answer is, as always, it depends, in the sense that if we work in the A point, the impedance is higher than the point B. So the circulating current for sure is lower than the point B. And so even the flux density is lower than the point B. But the frequency in the point A is higher than the point B. So higher switching losses, if any, and is higher the contribution to the core losses because it increases here. So concerning the magnetic, if we assume the change in the flux density is balanced between the change in frequency when we move from the point A to point B or vice versa, then the core losses stay the same, let's say approximately the same. And the A point continues to be the best because of its higher impedance. Now, this is the first example in which requirements are reported on the top. So we have an input voltage that varies between 32 and 52 volts, an output voltage of 12, output power of 25, with a maximum working frequency of 100 kHz. This is the first example of 3 examples we will make here this evening. According to these requirements, we have understood that higher inductance ratio means lower circulating currents. And at the same time, lower inductance ratio means lower frequency span to get to the same gain. Let's start by selecting the smaller inductor that I have called L1 equal to 100 millihenry, just as the initial starting point. And for this design, I choose a inductance ratio that is 9. So L2 is 900 millihenry. This is valid, or this is valid independently from the requirements that are reported on the top. Now, move the same way with the resonant capacitor. Actually, I have selected the inductor L1. I have selected the inductor L2. What about the resonant capacitor? The same. Let's choose a capacitor in a completely random way at the beginning, just at the beginning. So to do that, to select the capacitor, let's place a low tank resistor. Here is 1 ohm, for example, to select whatever capacitor value you want in the frequency range that is under study. Here, for example, I swept the capacitor from 10 pico to 10 milli, and I have selected this cap, 10 micro, okay? And I have done that independently from the requirements. So independently from the requirements, I have selected 3 random values for C, for L, and for smaller L, and for the greater L. For this tank, C1, L1, and L2, let's start by identify what is the maximum load condition. The maximum load condition is the same, is equivalent to say, let's identify the minimum tank resistor is the same. So actually with SPICE or equivalent simulator, you can check how for this LLC tank, the minimum tank resistor is 300 ohm. Actually, it's even slightly less if I do not remember wrong, is something like 220 or 230, something like that. But let's take some margin and let's keep 300 ohm. Why 300 ohm? Simply because it is the minimum resistor value for which we are able to guarantee the right behavior of the LLC. Remember, if the voltage falls, whatever root cause is, bus swing, load swing, whatever it is, we need to increase the gain. So if I go here for 200 ohms, for example, for sure I get a wrong behavior, because if the frequency decreases, the gain will decrease. Let's think about it. By the other hand, all resistor values higher than 300 ohms are okay, because for all of them, if the frequency decreases, the tank gain increase. So from this bunch of resistor, the lower one identifies let's say the best I can pick to mimic the heavy load condition. Big source of confusion here as well. What about the quality factor? So actually we understood that by sweeping the load, we have two resonance peaks. In related literature, the Q factor is more commonly expressed in terms of the higher resonance. But since in reality we travel along the curves of the lower frequency resonant peak, it is much more intuitive to fix Q based on the lower frequency resonant peak, not the higher. Despite you can read, let's say, 1000 up note that they say the opposite, but to me it's much more intuitive to fix Q on the lower resonance because you travel along that curve. So let me clarify this point better because it creates confusion. First, by sweeping the load, you see two resonances. The first source of confusion is to choose to which resonance does Q refer. So here I choose the low resonance because again I travel along that curve when I'm called to increase the gain. Second, without clarifying in which condition we get our quality factor, which load condition, be sure you can have infinite combinations. So point number one, define the reference resonance to which you are referring your quality factor. Point number two, define the load condition in which you are defining your quality factor. And then, and only then, we can talk about the quality factor. We can identify for our tank, so we have identified the 300 ohms as the 300 ohm as the best resistor which mimics the high load current. Here identify the best quality factor that is low resonance related. Once again, that is 1.054 at the maximum bus and maximum load. I repeat once again. Look, all the discussion made until now doesn't take care of the requirements that are reported on the top. So to properly map all the consideration made until now to our requirements, we will use the scaling laws. Let's start to be familiar with these terms because you will see in a while the power of this concept. Once we have identified the 300 ohm resistor as the best one which mimics the maximum load of our random LLC tank, let's choose the best design entry point. Here I call it as BEP, best entry point. The top graph refers to the voltage gain of our tank. The bottom graph refers to the input impedance phase of our tank. The blue curve is related to our LLC random seed charged with the 300 ohm resistor. We will discuss in a second the red plot, but just for now neglect the red plot. The dotted parts refer to the capacitive zone. The solid parts, the solid curves refer to the inductive zone. So for our tank, independently from the requirements, the best gain entry point at maximum bus, maximum load, is identified near the higher resonance. So slightly higher gain respect to 1. So here I took 5% margin, and slightly lower frequency respect to the higher resonance. It is the green circle. So please note how the blue curve offers a maximum gain of, here I did something like 1.18 at minimum frequency before going out the 0 voltage switching zone. Is it sufficient to match our requirements? Actually, no, it is not sufficient. For sake of clarifications, all main info are reported on the right. So this presentation, remember, that will be shared, so you can go through all the details you want. Everything is reported on the right. On this slide, I will go fast. For my LLC analysis, I'm using the first harmonic approximation. There is no sense to overcomplicate something that is tricky per se. So back to the bachelor's degree, we studied how to solve linear networks by using sinusoidal excitations, sinusoidal signal excitations. So using the first harmonic approximation simply means this: if you are called to solve a linear network excited by a non-sinusoidal signal, let's say, I don't know, square wave, triangle wave, sawtooth wave, and so on, an approximate solution can be evaluated by sourcing the same circuit with a sinusoid having a frequency that is equal to the one of the original frequency, and an amplitude that is equal to the one you get by using the Fourier transform of the original signal. The Fourier transform, obviously, of the non-sinusoidal source. For the LLC converter, we typically work with the first two waveforms reported enclosed in the red rectangle here. You can neglect for this presentation all the rest. Here, the reference book is the one by Mr. Stephen Smith, and I mean, there are tons of sources, so select the one you prefer. Let's make some calculations now, starting to include the bus swing in our random tank. If bus voltage is 52 volt, it means that the voltage on the tank output, so on the tank resistor, is 52 over 2. Why over 2? Because I'm using an half bridge stage. So if you use a full bridge, you don't need to place the ratio of 2. Multiplied by 4 over pi. 4 over pi takes into account the first harmonic approximation gain, multiplied by 1.05. So this multiplication gives the voltage on the output tank resistor, on the resistor. 1.05, I repeat, is identified as the best gain entry point at maximum bus, maximum load. If we reverse the criteria by locking the tank voltage to be something around, I see here, 35, and we run into our minimum bus condition, that is 32, we get that the required gain at minimum bus, simply by reversing the formula, should be increased to something around, should be something around 1.7. But we have seen before that our 300 ohm tank resistor, see the blue graph on the top, cannot give 1.7. I mean, it's able to give 1.7, but you are not able to assure 0 voltage switching. So the 300 ohm we have target initially is not enough, and we are forced to increase the tank resistor. Only in this case, we are able to get a higher gain, that is 1.7 in this case, that is the one we are looking for at minimum bus. And by increasing the tank resistor to something around 477, we are able to preserve the 0 voltage switching. Again, for sake of clarifications, all main info are reported on the right. So we have adapted the bus swing. So actually we took the random tank, we have selected the minimum resistor, which mimics the maximum load condition. We have tuned the resistor we selected initially with something that can match our bus condition. Actually, if we calculate the peak power on the tank resistor, so we are exciting our tank with the sinusoid, I'm going to calculate the peak power I'm getting on the tank resistor in both bus conditions. So if we do that, we get two different values, in the sense that if the voltage on the tank output is locked to be something around 34.7 volt, and the load resistor, the tank resistor, has been called to increase in order to match the requirements at minimum bus, Ohm's law suggests that it's okay to lock the tank output, but we are not able to transfer the same amount of power if the bus varies. So let's say, okay, I would like to get voltage regulation, but to get voltage regulation by swimming in the input voltage, the input bus, I cannot deliver the same amount of power because its Ohm's law is nothing special. Second lesson to bring home is, if we vary the input bus voltage to get voltage regulation, we cannot guarantee the same output power. So this is very important, because let's start to think about that. So we have a converter that is able to guarantee not a specific power, but different values of power. We will run into this in a while. So we started from a random LLC tank. We have identified the maximum load. We have identified the load to match our input bus swing. Now I'm including the power requirement slowly. Now, the power requirement is 25 watts. Actually, these 25 watts, to which bus condition is referring to? Maximum bus or minimum bus? The answer is simple here again, because for sure, if the power decreases with the bus, it is much better to target 25 watts at minimum bus, getting, let's say, a bigger power or a more deliverable power at maximum bus. Vice versa, if you target 25 watts at maximum bus, once we are called to decrease the input voltage, be sure that we are not able to deliver 25 watts, simply because of the peak power calculation we have made here. This slide collects the most important notes made until now. So in the first plot, we see, to guarantee a gain of 1.7 required at minimum bus, we need to increase the tank resistor to something that starts from 300. The tank resistor is placed on the x-axis. See, so we increase the tank resistor to something equal to 470, I don't know, 477. In the second plot, we see with this tank resistor value, we are able to reach the minimum fundamental sinusoidal signal we were looking for. What is this value? Is 32 from the requirements over 2, considering the gain of the alpha bridge, multiplying 4/5. And you get the same numbers I have reported here on the right. The third plot suggests the minimum working frequency. Why the minimum? Because we are working at maximum gain. We are working with the maximum gain. So the frequency span has been increased a bit. The fourth plot instead suggests the peak power reached with our tank, taking into account the voltage requirements. So we get a peak power of our tank that is 4 watts, and the peak power minimum that is 2.5 watts. As calculated, it's the same we have calculated in the previous slide. It's the same. It's just a summary table. Now, we understood how does the tank work. Let's place the second piece of the puzzle, introducing the input inverter stage. The input inverter stage can be divided in two main categories. Oops. That is, on the left, you see the full bridge with its first harmonic approximation. On the right, you see the full, sorry, the half bridge with its first harmonic approximation. Actually, you see that basically the 4/pi quantity is always present. And on the right here, I have reported some half-bridge variants. Actually, they work the same way as the classical half-bridge, identical in terms of first harmonic approximation, while the tank is excited in let's say, unipolar way, why it is excited in a bipolar way from the half-bridge and full-bridge reported on the left. Okay, so the one on the right in the blue box are just half-bridge variants. Okay, let's do the same for the output rectifier. Let's place then the third piece of the puzzle. All of them rectified voltage with pros and cons in terms of both, basically the transformer manufacturing and the diodes and the stresses on the diodes in terms of both the voltage and current stress. So let's go to these features quickly. So on the left, you see the full bridge rectifier. So here you have an easier magnetic from the manufacturing point of view, and use it for when you have high voltage and low currents. Why high voltage? Because you can split the voltage on the two diodes. On the right, you have the half bridge rectifier, and the magnetic is harder because here you need the center tap transformer. Use it for high currents and low voltage. Why for high currents? Because you have you split basically the output current in two branches, so you reduce the stress. The RAC concept needs to be understood deeply. It doesn't belong to the puzzle per se by the electrical schematic, but it has a critical impact in selecting the right transformer turn ratio. So RAC simply mimics the needed resistor to be placed at the input of the bridge section in order to transfer the same amount of power of the one which includes the rectifier bridge. So its value is calculated by balancing the power at the input section with alternating signals versus the power at the output section that you calculate by using DC signal. The power balancing equations are reported on the right for the RC resistor. And at the same time, which source do I need to use? Actually, the peak current amplitude closed formula, valid for both circuits, is reported below. So recall the load resistor differ between the two circuits by using the formula highlighted in yellow and reported on the right, while the input current generator is identical in both circuits and calculated with the formula reported in red here on the bottom left. So you can see that this comparison between these two circuits gives a very important information. First, that the DC power of both circuits measured at the output section is the same. Second, if we work with sinusoids, we need to target a peak power at the bridge input that is the double value of the one we were looking for in DC. So at the output, we have 25 watt DC. At the bridge input, we need to target 50 watt peak. So in which condition do we need to verify that? Again, surely at minimum bus, because we understood that at minimum bus, we are able to deliver less power. So if 25 watts DC is related to 50 watts peak at the input bridge and minimum bus, what is, again, the peak power we need to target at the bridge input if we work at the maximum bus? Simply by using a proportion. Simply by using the proportion. So here, we know that the power of the tank, the maximum one is 4, the minimum one is 2.3. This is DC power of our tank. we have calculated that we need 50 watts peak in this section here. So by simply using a proportion, you get that the peak power you need to target here at maximum bus is 80 watts. So 50 watts peak power, minimum bus, 80 watts peak power, maximum bus. Why it is important to do that? We will see it soon. Actually, we have built our LLC tank, we have placed the inverter stage, we have placed the secondary side. Actually, how we can link the two stages by placing the transformer. So again, how to get the turn ratio here? So we said that the voltage on the output of the tank, so this voltage here is something around 34.75. How we get this? Simply we come back, is 52 over 2 maximum bus over 2 because of the half bridge, first harmonic approximation gain, best gain entry point. We get this value at the output of the tank. What about the secondary? The secondary is easy because the secondary peak voltage is the input resistance at the bridge. By using these equations, you get the input voltage resistor, multiply the E peak secondary with E peak secondary. E peak secondary is the one we got here. So by simply getting the ratio between 34.7 over 15.3, we get the transformer turn ratio. Actually, you can use even the closed form formula. The closed form formula you see on the bottom right is simply obtained by considering all these passages here. It's a compact form that takes into account everything we made until now. So I suggest don't do all these passages I have done. This is just for clarifying and making and just to make things simple. But if you need to calculate the turn ratio, simply go straight forward with this formula here. Okay, you get the same. Actually, this, okay, do you remember that we pick LLC values randomly? So it's time to introduce the power scaling rules. Power scaling concept is the first important aspect of this presentation. It is, keep in mind that it is applicable to all topologies, always, anytime, whatever power stage you pick, whatever power stage you are designing. So if you combine these laws with the graphical approach, with the graphical approach I'll present later, you will get a very powerful tool. So let's go into this a bit. So to make the discussion simple, I took into account two buck converters. For both buck converters, the inductor and the capacitor formula are reported on the top here. They are both dependent from the current ripple ratio, that is the R parameter. The current ripple ratio is the ratio between the full delta swing AC component of the current, the full one, so 2 times this one, over the DC component. Actually, what happens if I have two buck converters, one with the power P, another one with the power 2 times bigger than the first one? You know that both circuits are getting voltage regulation. So here, if I'm doubling the power for the second buck, that is this one, actually I'm placing a factor 2 in the denominator here, because the voltage cannot change, the voltage is the same. We are getting voltage regulation. The power is double, so I place a 2 factor here, But to keep this equation an identity, I need to halve the capacitance, to halve the inductance. Again here, if I double the power, I am placing a 2-factor here in this position at the numerator. So to keep this equation an identity, I need to double the capacitor. What happens to the energy stored by the inductor? Actually, if I get the energy formula, I see that for the second buck converter, I get an energy store that is 2 times the initial buck, the one taken as baseline. So multiplying per 2 power means half value of the inductance, but bigger size. Bigger size. These 2 factors here is just taken as an example. You can place here 46, 50, 1000, etc. It's just to make the concept simple. What about the frequency? The same. These are the 2 formulas. So actually, if the second buck has a double frequency, I am placing a 2-factor here. So to keep this equation an identity, I need to halve this inductor. Same concept here. I'm placing a 2-factor, let's say X factor in the denominator of the capacitor formula. So I need to place a 2, to keep this equation an identity, I need to place a 2 here, so the capacitor should halve. What about the energy stored by the inductor? Actually, multiplying by 2 the frequency means the inductor decrease, while the size decrease because the energy is half versus the one I have calculated before. I leave this question for you. So what happens to the inductor if I double both the power and the frequency? What happens to the L value and to the L size? Let's think about it. Okay, so let's calculate now the frequency scaling factor. So our tank imposes a higher resonance that is something around 160 Hertz. While for our requirements, we have a maximum frequency that is something around 130 kilohertz. So the ratio between these 2 frequencies gives our frequency scaling factor to be 808. Oops, 808. 880, that is this one. Actually, the frequency scaling factor doesn't change in the sense that if you run into the same calculation by not keeping the maximum frequency ratio, but by keeping the minimum frequency ratio, you get the same value. And this is very important. You will see now why this is very important. Let's run into the power scaling factor. The power scaling factor again doesn't change like the frequency scaling factor. So it is calculated by considering the ratio between the peak power maximum at the input of the bridge section. You remember is this one. Is this one. The peak power here at maximum bus, that is 80. We have calculated it here. Or you can get the scaling power factor by getting the ratio between the minimum peak power, that was 50 because it was 25, two times at the input bridge section, so it was 50, over the minimum 1 peak power can be released by the tank. Now, let's calculate now our real values. So you can see they are reported on the left. So inductors always decrease with the power and the frequency, while capacitor increase proportionally to the power and inversely proportionally to the frequency. So on the right, you can see that even all resonances scale accordingly. This is a very important note. So before assembling all stages, remember to balance the transformer terminals on the schematic. And this point is layout critical and allows you to get a much more symmetrical circuit. Here we go with results at maximum bus. Note how we get a good voltage regulation with a maximum DC power that is equal to 40 watts. Here. Recall why 40 watts? Why 40 watts? Careful here. Why 40 watts? 40 watts because we have calculated 80 watts peak at the input bridge section. So when you switch beyond the rectifier stage, you get half-2. Be careful to the input generator here. This is a square wave with the amplitude scaled by a 2-factor. So here, taking into account the half-bridge inverter input stage. Let's move to the minimum bus. Here we go with the results. Note how we get a good voltage regulation with the minimum DC power that is equal to 25 watts. Be careful to the input generator here as well. One note is important, that the first harmonic approximation is not precise at the minimum bus, in the sense that the output voltage I have calculated at 53 kilohertz. So by performing our calculation was slightly high. So the controller corrected the frequency at something like 60 kilohertz, so 7 kilohertz more, to lower the tank gain. So if the output voltage is high, you need to decrease the gain. To decrease the gain, you need to increase the frequency. Okay, now this is a very, very tricky part. So power scaling concept is the first big deal you got from this presentation. Okay, graphical approach is the second one. I'll proceed slowly because it is not so intuitive without reporting step-by-step procedure. Okay, so it is something I use to increase the design speed further, and this will be published in the 3rd edition of the A to Z book. I'm typing with Sanjaya. As well as this book will include a lot of design tricks, so be careful on this. To get the maximum flexibility, this method needs to be combined with the scaling laws. So if we have understood that if we sweep the tank resistor of our initial LLC, looking at the input impedance phase, we see how the tank resistor increases when the minimum frequency, we have seen how the tank resistor increases. Then, let's say, the minimum frequency to get 0 voltage switching decreases. Is this one, is this graph. So, by sweeping this tank resistor, we are moving this way from right to left in terms of resistor. But you see that the minimum frequency that allow us to get 0 voltage switching tends to decrease. So if our tank resistor decrease, frequency, if our resistor increase, frequency decrease. So if I sketch these results I get here on a plot, I get that if the tank resistor increase, the minimum frequency to get 0 voltage switching decreases. So you get something like this. What happens to the gain of our tank? Actually, if I do the same job, we can see that once the tank resistor is called to increase, the gain is called to increase. So if you sketch the same results you get here on a plot in the same way we made on the plot on the bottom, we get something like this. So if the tank resistor increases, the maximum gain I get, that is this one in correspondence of the minimum frequency, tends to increase. Now, let's keep this in mind. We know that the output voltage on the tank can be calculated by the multiplication of the maximum input voltage and the minimum gain that we have identified as the best gain entry point. Or at the same time, we know that the output voltage on the tank can be calculated even by multiplying the minimum bus and the maximum gain. If we equate these two equations, I get that the voltage ratio, the input voltage ratio, is equal to the ratio between gains, the maximum gain over the minimum gain. So if I take this plot, the initial plot here, and I scale this plot for 1/0.5, that is my best gain entry point, I actually can think that here, this epsilon axis here is equivalent to the input voltage ratio. Is same, because I have the gain max over a constant value that doesn't change. So here I get the input voltage ratio. What about the frequency scaling factor? Actually, we know that the frequency scaling factor is given by, can be calculated in both ways, or by using the ratio between maximum frequency or by using the ratio between the minimum frequency. So here it is the maximum frequency by requirements over the maximum resonance frequency imposed by the tank, that is this one here. So if I multiply this plot I got at the beginning for the factor Kf, actually I'm able to get instantly the Kf factor, I'm able to get instantly the real minimum frequency I need, because this one has been got by focusing on the tank. But if I include the Kf factor here, actually, I'm reading the minimum frequency I'm working with. In a while, we will go with an example of that. What about the Kp factor? The Kp factor is given by the ratio between two power values. So I have the input power at each, the input peak power at the input of the peak power at the section that is the input at the section that is the bridge input over the one I get by my tank. So if I proceed with the calculation here, I get that this Kp factor can be obtained by the multiplications of two terms. One term that is air tank dependent, another term that is requirements dependent. You see, if I sketch even this plot here, I get that by increasing air tank, I get this parameter that is epsilon, I call it epsilon, multiplying this quantity here. Now the smart engineer will ask, okay, everything is clear, but what about the maximum frequency? I do the same. So if we zoom around this point, if we zoom in here, we see that by keeping always the same best gain and by sweeping the tank resistor, I get that the best frequency increases. So if I report these results on the second plot, you get something like that. What about zero current switching and zero voltage switching? Actually, the power of this approach is that basically both of them are assured because of the way I have extracted these plots here. We will run an example. Let's try a real example, okay? So here you see the same requirements reported on the top, but you get the same results of the previous 36 slides. So let's run into this quickly. On the plot number 1, left side, you see my initial random values L1, L2, and C1. Neglect for now the coupling factor. The coupling factor is just to increase the power of this approach even for wireless power transfer LLC. So for now, neglect this. From plot 1, I placed here the input voltage ratio, but remember that the input voltage ratio is equivalent to the gain ratio, no? So if this one is something around 1.75, so this value is around 1.72, that is 52/32. This value identifies the correct tank load resistor I need to take to place near I need to load my tank to get the maximum gain I'm looking for. So here is something around 474. Before was 477. So there is a MATLAB, let's say a MATLAB precision here that is much better this one, but the value is approximately the same. So this error tank value here locks the tank resistor and the x-axis on all the other plots. You see here. From the second plot, we get three main info. The first is the frequency scaling factor that is given by the ratio between the maximum frequency set, that is 140, over 160. Who is this 160? Is once again the resonance frequency imposed by L1 and C. So it's 1 over 2 pi square L1 C. Here, this value you can see here is something around 880. Is the same we got before. The effective maximum frequency, that is the blue plot here, is got by multiplying the epsilon value you read at this tank resistor over Fmax set. Again, the minimum effective frequency is got by taking the epsilon value you read on the second plot, red curve, multiplied by the Kf factor. It's something you read here. It's something you read here. So my working effective frequency maximum is this one, blue plot. The working minimum effective frequency is got by reading the red plot in correspondence of the tank resistor. No worries, guys, all the steps are reported on the right, so no worries. I mean, you can go through this deeply if you want, but everything is reported here. The third plot gives the power scaling factor, which I recall is composed by two terms, one dependent from the tank resistor only, and we take care of that by sweeping the tank resistor on the x-axis, and the other part that is dependent from the requirements. The reason why collecting both of them, you see on the epsilon axis of the third plot, output power and input voltage. Okay, the turn ratio can be got by recalling the closed form formula we got before, that is this one. The real LLC values can be got by using scaling laws. Remember that L, the inductor, always decreases if power and frequency increase, while the capacitor increases if the power increases and decreases if the frequency decreases. All calculated values here, where is my mouse? Here. All calculated values here are identical to the same values we got before. Identical. Now, I didn't report the simulation because they are equivalent to the previous case. Let's go to this example. These requirements have been extracted by a Facebook conversation, question made by our colleague that I translated like Ilya Hadiev. Not sure the translation is correct, but hope the translation is correct. The same graphical approach is presented here. This I'll not go through by step-by-step calculations, but all results in terms of best frequency range turn ratio, scaling factors are reported on the right. So one slide to fix all values you need. Simulation of LLC converter by Ilya Hadiev requirements. You see that at minimum bus, so I target these 40 kilowatts at minimum bus. You see that the simulation is okay. Just one note by my side, that remember that you're boosting the voltage, passing from 200, 400 to something like 800. So probably reversing zero voltage switching to the secondary and zero current switching to the primary could help, because if the output voltage is higher on the secondary with the same power, you get less current here. So it's better to have zero voltage switching on secondary and zero current switching on primary. Careful to the controller direction of correction. And let's consider even the possibility to use current sharing converters, so paralleling different converters. Now, Ray gave me different requirements that are reported here. So instead of targeting a maximum frequency, so he said, look, I would like to work with the minimum frequency that is 200 kilohertz. So this requirement is reported here. We know that the ratio between the high resonance and the lower resonance is this one. That brings this result here. So targeting a minimum frequency of 200 kilohertz simply means targeting a maximum frequency that is the minimum one multiplied this scaling value, whatever inductance ratio you pick. So here I select just to present you the power of the scaling laws and the graphical approach. I have changed the inductance ratio to something like 6. So the maximum frequency is something around 530 kilohertz. Look, these are resonances frequency, not working frequency. It means that our working frequency range will fall inside these two extrema, 530, 200 kilohertz. Remember always that we are decreasing the inductance ratio, so I expect higher circulating currents of the one circuit in which we have this ratio equal to 9, for example. Look here, same graphical approach, identical. I went directly with 3 plots. You see that I have completely selected random numbers for LLC seed with m equal to 6. You see random numbers here. All the passages are the same, almost the same. So you enter with the input voltage ratio that is 56/40. You identify the best tank resistor which is able to guarantee the maximum tank gain you need at 40. From the second plot, you get 3 info: the frequency scaling factor, the maximum working frequency looking at the blue plot, the minimum working frequency looking at the red plot, and the power scaling factor. So what happens if I change this value here? Inductor and capacitor values stay the same. They are the scaling factors that differ. So if you place, for example, here 6 Henry and 1 Henry, it's the same that getting an inductance ratio that is equal to 6. So you can try it by your own by selecting a completely random cell here. All the things that changes are just the scaling factors. Okay. Now, instead of being entangled in the proportion, how much power I can deliver at maximum bus, maximum, I mean, I don't want to go through all the previous calculations. So how can I do that in a quick way? Actually, we have demonstrated how the power scaling factor doesn't change, right? So if Ray gave me these requirements here, obviously I have targeted these 200 watts at minimum bus, so at 40. So what is the power I can source at bus at maximum bus? Easy with the graphical approach. I remember that the scaling factor is 107, something like that. So the minimum load resistor, which identifies the maximum load, is you can find it in correspondence of the knee of the plot number 1. It is something around 250. So in correspondence of 250, that is the maximum load I can get with the Ray converter, I get on the plot 3 let's say an epsilon value on the epsilon axis that is 453. Now you say, okay, and then is easy because the KP factor cannot change. The DC power cannot change. This value here cannot change. The only value can change is epsilon 2. That is this value here. So you get 300 watts. What about the resistor here? The resistor, let me switch back a bit just to give you a better grasp on that. I have identified before, always the Ray example, that the resistor I need 376 to get 200 watts is here. So this one is the resistor I need to guarantee the minimum power. Let's check if it is true from the graphical plot. If I go here with this value, I get 682. If I replace the formula, I get 200 watts. So look, in one slide, you can identify which LLC factors you're looking for by combining 3 plots only with the scaling laws. From the plot number 1, you identify the knee of the curve, checking what is the maximum load you can get. That is the minimum resistor. Getting 2 epsilon values here with the maximum resistor and with the minimum resistor, you can instantly check how much maximum power you can source to the load at the maximum bus. Easy, it's not complicated. Let's play with this graph and I'm more than sure that you get this concept easily. So the output power range is this one. So here is the simulation at maximum bus, maximum power. You can see it's 300 watts. Perfect condition on both zero voltage switching and zero current switching. Let's move to the minimum bus. Minimum bus, I got a drift between what I have calculated, 260 kilohertz, and the real frequency I needed to provide voltage regulation. Actually, once again, this is the second time in this presentation we have demonstrated, so we have checked that the first harmonic approximation is not precise at the minimum bus, because the output voltage at this frequency, the one I have calculated, was high. So the controller increased the frequency to reduce the gain, and the frequency at which the controller stabilized is 300 kilohertz approximately. So you can see that once I move far away the resonance, so once I work at the minimum bus and the maximum gain and the minimum frequency, you can see that the tank current, that is this one, the violet one, drifts from being purely sinusoidal. So once we move far away from the resonance point, this is the reason why tons of designs are tuned around the higher resonance. So working around the higher resonance gives you a much better shape, not much better, let's say it gives a better shape of this tank current that is much more similar to sinus, much less distorted respect this case. But that designs do not mention that working beyond the higher resonance means no zero current switch, so you have a better shape of the tank current, but you lose zero current switching, you work at very high frequency, you get much higher frequency span to get the same gain in amplitude, and you get much higher core losses because the frequency is higher. So which one is better depends from your application, but to me, to what is my experience, I prefer to work in the middle frequency range. Despite, I mean, there are tons of designs made in a different way, but they are not wrong. They are correct, but you lose some advantages. So what is the effective frequency and the available power at 52? So how can I check what happens at bus voltage at an input bus voltage that fall inside this extrema? Easy answer. We have the input voltage here. We have the effective frequency here. We have identified that the minimum bus, I'm able to deliver the lower power, 200 watts, working at minimum frequency, that is 300 kilohertz. We have identified the maximum bus condition 56, again with the maximum power I can deliver, and with the maximum working frequency. So by simply interpolating these 2 points, I get 2 equations, one for the frequency and one for the power. You get the same number of equations compared to the epsilon axis information you are looking for. So you can see that these are the 2 reference equations. At 52, the effective frequency is something around 420 kilohertz, at something around 270 watts. This is the answer. Now, let's push the graphical approach to the limit. What time is it? Just for curiosity.
It's 11:24.
So it's 1 hour and a half, right?
Yeah, if you could wrap up in about 5 minutes, that would be good. And then we could have some questions.
Okay, so let me, one moment, let me check here. Okay, let me close just this point. Okay, so basically this is the exploded approach of the graphical curves. I have split the minimum frequency vector and the maximum frequency vector, so the previous plot 2 in 2 plots, because otherwise it was too messy to understand. Actually, you can see here that in correspondence of the cusp of the second plot, you can differentiate between the LC series converter and the LLC converter. Actually, why that? Because basically, if I sweep the tank resistor from, look at the blue rectangle here, no? So if I sweep the tank resistor from, let's say, 10 to 200 ohm, the result is reported here. So actually, I'm not able to intersect the best gain entry point that I have a target to 1.05. No, so if I zoom in in this section, you can see how this behavior, despite strange, is true. It is true because I'm not able to intersect the gain I'm looking for. What happens here when I increase the frequency? This is the right behavior. So when the tank resistor increase, the maximum frequency vector increase because the best gain entry point kicks in. So this is the graphical approach tuned by considering different inductance ratio. So you have here M equal to 3, M equal to 6, M equal to 9. So you can see here how by decreasing the inductance ratio, you have different minimum frequency limit. I mean, this is referred to the frequency span, so you have an intuitive answer from here. Actually, what happens to the frequency scaling factor, power scaling factor, turn ratio, if the ratio of inductance vary? varies, sorry. Actually, nothing changed, everything stayed the same. So these curves used here are valid for the best gain entry point, either than 1. Because again, we have targeted the best gain entry point that is 1.05. Okay, so careful about that. If you decide to work beyond, so if you plan to work beyond the higher resonance, so targeting a best gain lower than 1, something like, let's say 0.8, 0.9, we did this job by our side. So this universal curve stays the same. Not probably identical in terms of the lower resistor side, this one, but the algorithm. I mean, the point is when you are called to sketch these curves, let's make the best gain entry point custom, in order that by simply switching it from 0.9 to, let's say, 1.1, we are able to get the curves you're looking for. Yes, we are at the end. These are some questions I received privately. So I'll go fast on this to give you the right time to answer, to preserve just some times to answer your question. So how to close the LLC loop? We need another webinar. Is something not so easy to do. Ray, obviously I give my availability to that if the feedback by our listener are positive. Is LLC always better? This question, to this question I have answered to Arthur maybe at the beginning. Always is nothing, because why the LLC is not always better? Actually, the problem is that first, fixed frequency converters are more easy to manage, are more easy to parallel by the system level. The LLC converter is much more complicated to synchronize at system level. So, I mean, use the LLC converter carefully. This is the point. It is very powerful converter, but is much harder to synchronize. What happens if I want to work beyond the higher resonance? Again, I discussed this point during the presentation. You lose zero current switching. It's true that you get lower RMS current, but you work with higher frequencies, so more losses. It depends by the design you need to do. Is this approach valid anyway, working beyond the high resonance? Yes, I answered to this question too. So respin universal curves for a lower gain, entry point 0.8, the one you're looking for, but the universal curve approach stays valid anyway. So what about the other resonant topologies combo? Actually, there are a lot of possible combinations, LLC, LCC, CRC, and so on. So we discussed just the first topology. So Ray, if I would like to jump to the last slide, because there is no, let's say, sufficient time to discuss the design when the gain is lower than 1. So my ending notes are reported here. Check always zero voltage switching and zero current switching. Look at the waveform by simulation. You can see that there is no particular math needed, just Ohm's law in terms of voltage current and in terms of power. This is a very, let's say, important sentence I found on this book, on chapter 4. So when you see on the up note too much maths, too much equations, too much something, it is not the right up note, because for the LLC design, you don't need something complicated. Sweeping at a tank, the tank resistor, not the frequency, the tank resistor gives much more information about what you're looking for, and combine this plot with the scaling laws. Last but not least, I need to thank Ray for this occasion. I mean, you gave me this chance to talk to our colleagues. You know, to me, you are one of the greater icons in this field. So thanks for that. Thanks for hosting me. And thanks for your contribution to our world. So you can find here, guys, the 2 links to the Power Supply Design Center Facebook group. So if you didn't done yet, please join, because you can learn a lot. I invite you to check the Ridley Engineering. There are a lot of useful articles in there. And that's it. Stay tuned, because the A to Z book, 3rd edition, is coming. There are a lot of tricks, graphical tricks, curves, modeling in there. This book is something that I'm typing with Sanjaya. Sanjaya is going to do let's say the higher effort in that. I'm giving just my contribution. Complex math forbidden on this book. Everything will be discussed with a completely different cut and making it easy for the reader. That's it. Open for the question, and thanks for your attention.
Yeah, thanks so much, Nicola, for that. That was an awesome presentation. If you look at the questions there, you'll see we've got about 10 questions queued up. One of the more important one was, can they get the script for doing these curves? I know that was in your presentation on Rev 6, and then you took that out, so I don't know where you stand on that right now.
This is a hard question. This is another question. Let me think about that. I'm not able to give you a quick answer now. So I'm able to share the plots, but due to the fact that this routine will be included in the book, I need to check with Sanjaya first, and I will give you a feedback on that. So no problem to share the verbs in terms of image, but in terms of the C script, let me think about that. I do not have a clear answer.
Okay, thanks. There was another question. Can you see the questions there, Nicola?
Let me check.
The first early question there is, yes, we will do an LLC control webinar. We'll schedule that for first quarter next year. So perhaps February.
Okay. Let me add just one detail on this question about the C script. Guys, I think the answer will be yes, but just let me cross check this point. Okay, no problem. Anyway, I'll try to do my best. No problem on that. Concerning the LLC control, I'm able to do that. Yes, simply let me know just sometimes before, because I'll try to close the loop for one of the example presented. No problem on that.
Okay, great.
Mallory's question.
Actually, I don't know why my window for the question is very small, and I'm not able to see all the questions clearly, honestly.
All right, there's lots of congratulations and thank yous. Which circuit simulator did you use in the presentation?
Yes, this is a good question. Actually, I discussed at this point even on the group. I have checked that there is even the best focal point about this presentation was involved here in the webinar. I have seen his name. So the simulator is Tina Design Soft. So the focal point is Mr. Michael Koltai. So contact him directly. I have seen that he joined this webinar. So I actually think that I'm using this version here of Tina in its free evaluation, but I can say that the industrial version is really, really powerful. So ask for a demo and you will confirm or not.
Someone has asked whether you're going to do an LCC circuit webinar.
Yeah, LCC, good question. LCC can be studied by using the same identical approach. Actually, what I have found is just a little spoiler. With the same power, I found the LCC less efficient. But what we can do is, what you can do if you want is to go through the same curves. So simply charge the LCC with the tank resistor. Let's sweep your tank, and you have instantly the parameters. Then by using the parameters with the same power, you can cross-check, at least by simulation point of view, which one is better, which one is not. It's not an easy question, this one.
Yeah. There was another question about the duty cycle of the switches. And correct me if you're wrong, but everything is 50% duty cycle on the switches here, and the subject of changing the duty cycle of the switches just gets us into another level of control. Is that correct?
Yes, correct. Correct. These designs are based on the fact that yes, the half bridge are controlled by using 0.5 duty.
Lots of questions here. I'm parsing it.
No problem, no problem. I'm here. Happy to, if I'm able to answer, I'll answer without problems. But there is a chance that I'm not able to answer sometimes. So
yeah, there's a question here. Somebody asking for master's students who are looking to become good designers, what should they do?
I didn't get the question, sorry. What do the students need to do to become good designers? Guys, I suggest to read the right amount of upload, and let's go on the lab directly, because you learn just if you break something. This is my positive feedback. It's not a shame to me to say this in public, but I have started to, just for example, I have started to manage GANFET by destroying a lot of boards. This is just an example. So to become a good designer, you need to read less and read the right things, because sometimes there is tons of documentation, but just a few amount is the right one. And let's go to the lab. This is my advice. Hopefully, by learning from the other errors. If you are able to learn from the other errors without breaking nothing, it is much better.
Yeah, I think another comment on that is the approach that's being used here to work with curves and some experimentation in the design process is so much better than trying to work with the raw equations you're going to find in the academic field. This is the way designers work. When you're a master's student, you're just analyzing. All you do is analyzing, and you don't learn how to design. So same thing he just said. Go build things, design them, simulate them, of course, but blow it up. That's when you learn.
Yeah.
I'm sorry. One more question. They didn't catch the simulator. I think you said Tina.
Is called Tina, is T-I-N-A from Design Soft.
And that's the one that TI uses, right?
Correct.
And I think they're shifting to something else now.
I like this one.
Yeah, TI I think has made a corporate decision to go to some version of PSpice.
Oh, it's up to them. Actually, I find that honestly, I take the occasion to spend some words, because at that time I should have been able to justify why buy Tina that time, because Spice was available. I honestly find it much more powerful. I guess, guys, there is a related conversation, a related topic on Facebook group, in which I have identified at least 7-8 advantages respect the classical Spice. But go there, and I again simply try a demo, and then you can make your choice. You can continue to use LT Spice that is free, so it's up to you.
Nicola,
That's
ask the
fine.
adjustment range.
What's that?
Ask him about the adjustment range.
Uh,
That's Bill Mallory's question.
yeah, somebody asked about the adjustment range on the output voltage as opposed to the input voltage.
The adjustment of the output voltage is a very tricky topic, simply because it depends. For example, when you are not designing a voltage regulator, but you, for example, when you design a battery charger, for example, I don't know, I take my field as reference, but there are tons of design of a situation in which you can get huge swing. Actually, if you consider battery chargers in automotive, for example, they have huge output voltage swing, something like from 250 volts to maybe more than 400. So we are talking about very huge bus swing. So the thing you can do is to work as much as possible near the resonance. It means that you have 2 degrees of freedom, or you can work with the output PFC voltage, because playing with the output PFC voltage, so the input bus of the LLC, you are able to play even with the frequency, and you can modulate the gain you want. So the trick is to stay near as much as possible the resonance. This is the trick. Consider also that when you have huge output voltage variation, sometimes you are called to involve parallel modules. So probably the LLC is not the best choice if you are using current sharing converters. But again, if you are designing the LLC as a single module per se, maybe in that condition, when the output voltage varies, it could be better to work even beyond the resonance. But again, depends from the application.
Somebody asked to see an LLC magnetic. I got one sitting on my bench here. You can see that.
Guys, I see it.
I don't know if that helps, but the only point is there, the most part,
actually,
they separate the transformer and the inductor into 2 parts. So that's the one I have sitting around.
Yeah, just two advices for the guys. First, the LLC works in the same fashion of the forward converter. So everything you have studied for the forward magnetic works identically for the LLC. Another point is that for low powers, probably less than 1 kilowatt, you should be able to include the leakage inside the transformers. But I mean, if the power goes high, you are called to split the both magnetics. But in terms of behavior, let's make things easy and use the same forward concept. I mean, the LLC transformer doesn't store nothing, no, in the sense that due to the fact due to the nature in which the windings of the LLC are rounded around the core, the only thing that the magnetic stores is just the magnetizing inductance, but there is not the same effect you get on the flyback, no. So you can use the same concept you use for the forward converter, magnetic.
Are there any special gate drive techniques used for the LLC?
No, there are no so different respect to the classical one. Just the note that deserves importance is the modulator. I mean, in the sense, you have the modulator, you have the modulator section, you have the gate drive section, and then you have the power switch. So in terms of gate drive, there are not so high challenge in respect the classical stage you have used for fixed frequency converters. It's the modulator that differ, but the gate drives in terms of I don't know, fast turn off, or let's say it's the gate drive section is not so different by the fixed frequency converters. This is my personal experience.
And what's your preferred method of gate drive? Transformers, high side drivers, digital isolation?
No, you can use different methods. You can use there is no there is no preferred method, because sometimes you prefer something, but for that application doesn't work. So you can use magnetic driving. You can use, I don't know, bootstrap driving. I mean, there are different methods. So there is not something that I prefer or I don't prefer. There is something that works better than something else.
Yep. When we do our design reviews, we see everything in terms of gate drive. So no definitive answer on that yet. Let's see. Somebody asked about how you incorporate the output capacitance of the FET into your design process.
How do you? I didn't get. I didn't get the question, sorry.
The output capacitance of the FET, the COSS.
Yeah,
do you
simply
account for that?
Yes. Yeah, simply, guys, is always the same thing, in the sense that simply you can choose the powers, the power device you want, You can design the LLC to work in inductive zone, but be careful to guarantee the right amount of dead time you need to discharge that capacitor. So, you know, there is nothing complicated. It is E, is C, the B on the T. It's always the same. There is nothing complicated. So be careful to use the right amount of dead time to discharge that capacitor. H cap answers to the same equations. There is no way to demystify or overcomplicate something that is not complicated. It's a capacitor. It's not linear, I agree, but it's a capacitor.
Somebody asks about using a two-bridge LLC. I assume they mean two in parallel. What difficulties might you run in?
The synchronization for sure. The synchronization for sure, because I went into this in the past, and I found very hard to synchronize to LLC converter, while I found very easy to synchronize fixed frequency converter. So again, if you build something that could be subjected to be paralleled in the future, go straight for a fixed frequency converter. I'm not saying that it is not possible, but for example, if I'm working on let's say on an onboard charger of 6 kilowatts, and in 1 year they are asking about 12 kilowatts, I will never go for LLC once again.
Yeah, one of the interesting.
Do you agree with me, or you can design directly one module 12 kilowatts LLC? In this way, yes.
Yeah, I wouldn't argue with that. One of the interesting things you run into with parallel LLCs that you may not anticipate is that they are bidirectional. And then you can have one converter processing in one direction and the other one sending the power back to the primary. So you have to make sure your control is taking care of that too.
Yeah, for sure. The bidirectionality is very interesting behavior, but again, keep in mind that the control is very, very tricky if you move with bidirectional LLC. At this point, it's much better to move for the dub directly because you can get the zero voltage switching as well, and it's fixed frequency converter. So do not overcomplicate something that is complicated per se.
Mm-hmm.
So keep in mind that when you're calling to make the design, sometimes you have a time schedule. So despite you can build the best converter ever, keep in mind that you should be able to keep it working on the bench. So you can design the LLC ultra plus stronger, but when you go on the bench, it is very hard to debug. So I suggest, in particular with bidirectionality, again, it's not something that it is not possible to do, but makes things easy. Let's go for the dub in that way.
I'm sorry, go for the what?
Get from the DAB.
Dual active bridge.
Yeah.
Okay. Maybe you'd like to do a seminar on that one too.
Yeah, I will able to do that. No problem.
No, Jonathan Brown, I'm not saying don't run them in parallel. Just be ready for trouble and be careful.
Yeah.
Are the modulators purely hardware or is firmware needed? I think that's a digital analog controller question.
If you are running with the unidirectional, it is much better to do analog, but just because you can close the design by your own. But if you go, for example, there are the modulators from, I have used the NCP from onsemi in the past. I mean, the behavior was good, nothing complicated. But again, if you are going for something bidirectional, maybe it's much better to use something like C2000 from TI or something digital, because you need to control 8 switches, and when you parallel modules, maybe you need to control 16 switches. So with analog, it's not so easy.
Somebody's asking what happens on power up. Do you have a worry about the stresses on the switches and capacitors as it goes through the resonance and tries to get started?
About the stress, may you elaborate a bit? I didn't catch.
When you're first trying to get the converter started, what about the stresses on the semiconductors and the switches?
So actually, the startup phase can be easily managed because you can guarantee a lower start of the converter. I mean, there are different ways to do that, but this is one of the stress on the switches is just part of the problem. I mean, when you start the power stage, there are even added problems, maybe more complicated to fix, such as the inrush problems. So it's easy to control the soft start of the LLC, but actually I didn't get any particular troubles on that. So simply take care to guarantee a soft start of the right amount. Let's guarantee the right pre-charge time and keeps the right attention to the transition, let's say to the transition from zero charge to steady state condition. But it's not something that makes me troubles in the past.
Another question is about the topology of the primary, whether you use the split capacitors. I think you showed a couple of variations there, and I think there's some more as well.
Yeah, concerning the split capacitor is simply a way to optimize the alpha bridge topology. Actually, you get with the split capacitor, you can get lower current on the bus. You can guarantee less power for each cap with the same requirements, same current. This is point number 2. Point number 3 is that you can provide it's easy to provide over voltage protection by using splitting caps, because you can even parallel something else into the caps and you can provide the over voltage protection. So there are some advantages on that. So point number 1, lower current on the bus. Point number 2, lower power for each cap, despite the total one stay the same. Point number 3, it is much easier to get, not easier, but they allow you to build something in parallel to guarantee over voltage protection. So it is something that I approve.
And somebody's asking questions about parallel LLC converters. I'm not sure what that means.
What is the meaning?
Of a parallel LLC. I mean, it's kind of series and parallel, right?
But parallel, 2 modules parallel or a different tank configuration?
That I'm not sure on that. So, oh, he means 2 converters in parallel. There you go. I think we covered that.
Yeah, it's always the same, guys. When you need to parallel, be careful to use LLC. You can do that, and then we can keep in touch.
Is there a preferred core type? Somebody's asked about PQ, and somebody's asked about planars.
PQ is the cheaper. So the answer is let's say, is obvious, but I mean, I like, maybe not in the automotive sector, but I like planar approach a lot, despite sometimes is not convenient. The answer about preferred core is for sure PQ, because it's cheaper. So if you propose something expensive to your boss, you will get a rejection. So it's a core.
Getting back to the duty cycle of the switches, would you recommend reducing the duty cycle to get more range without the frequency range shifting so much? I know some papers have been written about that.
I have never used this approach, honestly, to reduce the duty cycle. So actually, I don't know precisely what he's referring to. May you elaborate a bit on this? I mean, decreasing the duty cycle of the LLC is something I have never used. Is something new, or?
Yeah, I think there's some papers on that for welding supplies and things, just for the range of loads that you might see. They would just have a dead time between the 2 switches, a long dead time. So change the content of the harmonic, I guess, but I don't know much about it either.
Yeah.
No,
me too. In the sense, me too. In the sense that actually I would like to answer, but I have never used this approach. But I'll go through this just to check what is the meaning of that.
Okay.
I mean, which kind of advantages do you get by reducing the duty? Because if you are overcomplicating, or I mean, I don't know. I need to check.
Yeah, I don't see how you maintain the 0 current, 0 voltage if you do that, because you've got that uncontrolled time there where it's going to be ringing. But again, there are papers about that. What about Chuck converters?
What about?
Chuck converters.
No, guys, don't ask me these questions in public. Please,
Right.
please. I mean, I can type privately to the person the person who answered this, but actually, let's answer this way. It's a good converter, but you can get the same performance, maybe better, with a much easier topology. Hope to have been clear.
There you go. Somebody's not convenient to do planar. I mean, there's nothing magical from my point of view about planars. It's just a question of how you build them with foil or circuit boards or wires. But a planar is a transformer to me. Do you have any comments?
It's more expensive for sure, and it depends how much do you gain in terms of efficiency, in terms of control of the parasitics. So I like the planar because of different advantages, despite sometimes they are presented like something overrated a bit. The problem is this: if you need to design a power stage in which your magnetics cost €1 with 90% efficiency, let's say, and you can choose for a magnetics that costs €10 with 95% efficiency, I will go always for the one that is cheaper. So I like planar, but the cost is high. In particular, if you move for matrix transformers.
Well,
I don't know if you have asked.
That's another topic completely, isn't it? The matrix transformers, because the highest density that we're seeing on converters is using planar matrix transformers with foils in them. They're not easy to build. They're certainly inconvenient, but for performance can be amazing on those. But that's again, another webinar for that one. Well, I think we've reached the end of the questions here. Still got 200 people in the room. So do read the new book that comes out, where Nicola is going to be writing that with Sanjay. Come to our website. And if you want to talk to Nicola, converse with him, everything happens on the Facebook Power Supply Design Center group. And if you downloaded the notes for this course, you have the PDF link to, the active link to go join that. Yeah, and yeah, I know it's Facebook, but that's where the most interesting conversations are actually happening. And we look forward to seeing you there. So thank you so much, Nicola, for doing this. This was great. Wish you and everybody a great holiday, happy Christmas, whatever you celebrate. And we'll see you all back in about a month, I think, with some other interesting topics. And thanks everyone for coming along. Thank you. And we will have a recording of this in, within a day or so. It'll be posted on our website. Okay?
Okay, thanks. Pleasure by my side.
Thanks so much. Bye. Okay. Bye, everybody. Bye.
Bye-bye.